Today, we are going to talk about rebuilding an industry, a legacy industry, from first principles. My talk is about re-architecting maritime, starting with the first principles. Now, I was never interested in easy machines. I started my career in particle physics. Then I moved to doing autonomous aircrafts. Then I did nuclear reactors. And at MIT, I designed underwater drones for ocean mapping. All very different industries and very different problems. But there is a common thread. It's about how do you control such complex machines in such unforgiving environment? So after I graduated and built this boat with my team, people who saw this were like, well, did you give up hard tech to build a fancy boat? Well, I get it. It's a pretty good-looking boat. But no, I did not give up hard tech, and this is not about a boat. I went into this to address a pretty ugly problem, the inefficiency in maritime industry. And what you see here is actually, I would say, a physics platform, like using modern tools, addressing hydrodynamics with controls, software, computing, and advanced materials, all integrated by really advanced software. So this is actually just a platform. And sometimes when you solve physics right, you do see that the result often can be beautiful. Now, of course, physics applies no matter what you carry in a boat, and therefore this boat applies across many disciplines, whether this is recreational, defense, commercial. It's just what you're carrying, but the physics doesn't change. So maritime moves the world. It's an old industry, and so many things have changed, but the architecture of the vessel hasn't undergone much evolution, although we have seen that in auto, in space, in aircrafts, even in computing. And when you look at this industry, it is really dominated by bespoke builds that are one-offs, and it's pretty inefficient. So there's high operational cost, labor cost, maintenance cost, and then, of course, we cannot scale things very easily here. But when you really think about it, the problem is not about building a better boat. The problem is the architecture of the industry itself. And architecture determines scale. In maritime in particular, scale is not just about economics. It is about strategic power. So the question is, rather uncomfortable question, is that who can build this at scale? So America was really good at this. We once built ships at scale. We built lots and lots of ships, rather thousands of ships during World War II. We were leading this, the Liberty ships. And then post-war, we somehow atrophied this muscle of building. When you look at numbers today, this is what we see. We have gone from a superpower to a bystander when it comes to maritime. We actually do less than 1% of the world's shipbuilding and controlling shipping. It's China who does more than 50% of it. Thousands of boats, we do a few ocean-going vessels. So recently, we have been looking a lot at shipbuilding. Over the past year, the administration has been talking a lot about, hey, we need to revive this industry. But we cannot win in this industry trying to imitate what others are doing. I think that's a trap. Copying what others are good at will not get us ahead. We have to actually step back and understand what are we good at. Now, there are two kinds of conversation that we have to get away from large, exquisite ships. All our competitors are building all these drone boats at large scale, and they're doing it so fast, they're putting it out there. Gosh, we got to do the same. But is that a right decision. You cannot really, outnumber China or somebody that quickly. We just don't know how to do it. But we are trying to play that game. If you step back a bit, you will realize that in maritime, the hard problem is not arriving somewhere. The hard problem is staying. And what I mean by that, most of the maritime missions are not this one-off events about strikes. It's actually about persistence. It's about presence, whether that is logistics, ISR, shipping, right, transportation. It is about having continuous presence at the sea. So I don't think, contrary to a lot of the conversation today, which is about like attritable, low-cost drone boats, I think the focus should be build vessels that can have long presence or persistence, low cost enough to scale, but reliable enough to stay. And that should be a key focus. So if I step back a bit and forget about copying others and really say, OK, I'm going to go back to the drawing board, and if I could start a maritime company today, no priors, how would I think of it from the first principle? What does a winning marine platform, what does it look like? So what we find is that it is at this intersection of these three things. Economics, which is low cost, not just to build. Everybody talks about low cost boats, but cannot be about just building the boats. Low cost to build, scale, and operate. That's the intersection of three things, which is a much harder problem to solve. Now, the second one is that you want vessels that are long range, at speed, not at low speed, right? That's also a hard problem to solve. They don't go hand in hand. The third is, what we talked about, is persistence. You want vessels that can be reliable, adaptable to sea states, and can have presence. Now, when you look at this intersection of these three, it's a hard problem, that holy grail, because traditional vessels, cannot satisfy this. This is not solvable. If you have a traditional vessel, if you want long range, you can put a lot more fuel, and that just increases your cost, right? And if you want speed, then it decreases your range. You want to lower your costs, well, then you get a not very reliable vessel. So this is not about, trying to improve what we have today. We have to step back and start ground up from the physics of it. So everybody talks about low-cost boats, low-cost drones, right? But when you really look at any of these programs, actually 70% often of most of these scalable vessels, that's actually your operational cost over the lifetime. And we don't hear much about it. So let's say our adversary have 10 boats, and we have 10 boats. But if our 10 boats have 5 times less operational cost, now that's innovation. We are not fighting head-to-head. We are fighting on a different game, and the game of innovation. So when it comes to operation, it is actually about physics of water. That's what drives the big part of the operational cost, because you have a boat, and that's trying to push water, which is 1,000 times heavier, almost, than air. It requires a lot of energy. The question is, why should we push water when we can glide above the water? If you look at a drag equation, right, it scales with your rated area. It also goes as the square of your velocity, and it goes with your density. So if I could get most of the surface area of the boat out of the water, you can drastically reduce your drag and become very, very efficient. And so hydrofoils really matter. What you see here is a hydrofoiling vessel, actually, more specifically, actively controlled hydrofoil vessel. And hydrofoil is not about just making the boat fly. It's cool to make a boat fly. But what is cooler is that I'm reducing per unit mile drag tax on this boat, and therefore I'm increasing efficiency. But there's some cherry on the top. It's also much more stable, much more reliable in many ways, and if you're in defense, then you know this is much, can be what I would call stealth, a low signature, very little areas under the water. Now, many of you will say, well, hydrofoils isn't really new. I mean, it has existed from 1900s. So what is really new about all this? We have tried it. It has failed. It's not great. It just breaks. Yes, all of that is true. So what has changed? What has changed is the control stack. I mean, we have gone from this really maintenance-heavy Boeing foil jet or the Pegasus, for the Navy, to today having, when it comes to computing, sensing, scalable manufacturing, and propulsion, all of that has been simplified. And that's enabling us to build reliable, scalable hydrofoiling platforms that we could not do before. What will the future look like, or what can it look like? I think the interesting part is the shift. I mean, so far, when we talk about marine vessels, I think all of you think about a ferry boat being different than a cargo ship, that being different from the defense, and we are also kind of biased towards what we see visually. So if we see a very beautiful looking boat, like the boat that I just saw, thinking of that as a defense boat doesn't come naturally to us, so we are like, well, that's a luxury thing. But if we can go back and really think about what is the core purpose of a vessel, the core purpose is to move per unit payload, per unit mile, do so reliably, efficiently. If we think that way, we can standardize the core, the physics, right? That's your hull, that's your controls, that's your foil, that's the system. That is what's enabling to reduce, your drag, sea state stability, and scale. The second layer is much more modular, which is more swappable, I would say, which is your propulsion. It can be electric or it can be hybrid. Now, once you have done this too, the third layer is your intelligence, which, you can be an autonomous vessel, you can be a manned, you can be optionally manned, that is remote. And this is all the software layer that, allows you to scale, to monitor your fleets, and, remote diagnostics and whatnot. And finally, it is a superstructure, what you call the mission layer, whether you put ferry, whether it is people, payloads, goods, you name it, but it's just weight, mass, right? That's on the top layer. So this is how we see that the future, when you think about standardization and scalability, should look like. Now, we talked about reliability. This is a very important part, right? For having persistent presence, you need vessels to be reliable. And as we all know, boats do not have their reputation. They break all the time, whether that's the aircraft carrier or whether that's your recreational boat. And that is something we have to double down when we think of how it is done in aerospace. And reliability is not something that is a fifth layer. It is actually something that runs through all of these layers. For example, hydrofoiling, which means that you're not slamming the hulls, means that you have less mechanical vibration, and so things don't fail as much. Similarly, when you're thinking of your architecture, how not to have a single point failure, that is also important. How to have simplified propulsion, maybe not do shaft drive, but underwater pods. These are all the decision making that stacks up together to give you the reliability. But that should be in every layer, not just one. Now, we hear about autonomy a lot. Everybody is about autonomous boats. It's cool. It's needed. But autonomy on an inefficient hull, that's slamming, right, in the waves, like that. I mean, think about it. You mount some payload. Can you really point well while you're trying to take down a drone or any target? When you have the Navy SEALs on them, they have a back injury, right? And we all have heard that story. Now, if this boat breaks a lot and it's not stable, it's expensive to run, what's the point of putting an autonomy on this inefficient machine? It's just autonomous inefficiency. That's what I call it. So it's an important layer. It's a multiplier, but not the foundation. The point is that great software does not fix physics, but also physics without good software does not lead to an intelligent fleet. So we need both. The future really is dual use, and I'm not saying it's dual use because it's a fancy word. It's because just what we saw, that if you strip down to the physics of it and remember what is the core purpose of a vessel, is to power payload and move it. So if you really want to scale, you want to standardize it. And this is how you lower the build cost. We have seen it in every industry, right? I mean, very simply speaking, the same computing chip that runs in the laptop that a student has is the same that is in a laptop that somebody in an enterprise company is using, somebody in defense is using. What matters is how much computational power is needed. So if you think through that, these vessels you can scale the platforms, but you can scale it depending on the requirement, range, payload, and so on. What we really should focus in maritime is really the standardization of the platform and really focusing on the core requirements. Something that I would love for you to think and go home with when you think of the oceans. It's a wild place out there. Not simple. Things break. But the ocean rewards physics, and it rewards reliability. And the ocean rewards presence. And at sea, persistence is a product. Thank you very much.